Okay, so this is the fourth lecture in this series of the mathematical prerequisites for quantum mechanics, and this is probably the last of the four lectures. At least that's how I've planned it to be. This is where we come to the culmination of all the linear algebra that we've been learning so far, and we are going to be discussing one of the most useful and most important things that we need for quantum mechanics, and this is called the eigenvalue problem. So I'm guessing you have learnt in your math methods course how one goes about calculating eigenvalues. So I'll first give you a little bit of a geometrical feel, like an intuitive feel of what exactly is happening when you're calculating eigenvalues and eigenvectors. In the last video lecture, we introduced operators, linear operators on a vector space. So these are, you can think of them as a matrix. Suppose, again, for a simple example, suppose I'm talking about the two-dimensional vector space R2, and on this vector space you can have various vectors. So let's take this vector, let's call it V, and a linear operator is a matrix. Let's call this matrix omega. So it's a 2 cross 2 matrix which acts on the vectors. So I can represent the vector V as a 2 cross 1 matrix. So when a 2 cross 2 matrix acts on a 2 cross 1 column vector, you are going to get some other 2 cross 1 column vector. Let's call this V prime. So we say that the operator omega has acted on V and turned it into another vector V prime. And depending on what omega looks like, geometrically you can think of this operation as either being a stretching or shrinking. You can think of it as being a rotation. You can think of it as being a reflection or a flip. So different operators will do different things. What I am interested in finding out is, given this operator omega will stretch certain vectors, it will rotate certain vectors, it will flip certain vectors. I want to ask, what are those vectors that only get stretched? By omega. By the way, when I say stretched, it could also mean shrunk, okay? Because stretching means you're taking a vector and multiplying it by some large number. Shrinking is, again, you're multiplying it by some small number. But basically it is just a vector V which is going to some constant times V. This is stretching or shrinking depending on whether k is greater than 1 or less than 1. So the question I'm asking is, what are those vectors which only get stretched or shrunk by omega? They don't get rotated or flipped or anything of that sort. Those vectors are called the eigenvectors of omega. And the amount of stretching or shrinking that happens, this constant k, is called the eigenvalue. Okay, so basically, given any kind of operator, here we're talking about matrix operators, we want to find out what are those vectors or those directions in your vector space which will only get stretched or shrunk and not rotated or flipped. That is what we mean by trying to find the eigenvectors of a given operator. So let's try and look at some simple examples. Suppose I take the operator, the simplest operator that I can think of is just the identity operator. So think about it. Do you know any vector V which, when it is acted upon by this identity operator, just gives you some constant times that same vector? Means it has only stretched or shrunk? Well, yes. This is true for all vectors. Any vector, if you multiply by the identity matrix, you just get back the same vector. So this k is basically equal to 1, the number 1. So all vectors are eigenvectors of the identity matrix, and the eigenvalue is 1. Let's take one more example. Let's take a matrix that is diagonal. So for simple, I'll take a 3 cross 3 matrix over here. So if I take a vector, my operator omega over here is, let's say, 2, -1, 5, and everywhere else is 0. So this is a diagonal matrix. I want to ask the question, is there any vector v, let's call it x, y, z, which when acted upon by omega just gives me some constant k times the same vector x, y, z. So you can play around with it a little bit. I'll give you the answer right away. Suppose you take the vector 1, 0, 0, and if you operate on this with this 2, -1, 5, you'll find that this will just give you 2 times 1, 0, 0. Right? Just do the matrix multiplication and check. Therefore, I'll say that 1, 0, 0 is an eigenvector of this matrix omega that I have written. And what is the eigenvalue? Eigenvalue is this number over here, 2. Similarly, try it out. If you take the vector 0, 1, 0, you will find that this is also an eigenvector of omega with eigenvalue -1. And try this out as well. Take a third vector 0, 0, 1, and you'll find that this is also an eigenvector with eigenvalue -5. So take this matrix omega, operate it on each of these vectors, and see that you're getting back the same vector except multiplied by this number 2, this number -1, and this number 5. So these are the eigenvectors of omega and the corresponding eigenvalues. In the previous few lectures, I have also spoken about, I think I spoke about, did I talk about operators as not necessarily being matrices, but in terms of functions? I may or may not have. Anyway, so I can talk about an operator. So this is the third example. So let's step back a bit. So if I'm taking the vector space of functions, and I'm going to define an operator. Suppose my operator is a derivative operator, d by dx. So I want to find those vectors, means those functions, which when operated on by the derivative operator give back the same function, at most multiplied by a constant. So here the eigenvalue equation looks like d by dx operating on some vector f has to give me some constant times that vector f. Do you know any such functions? Well, this is just a differential equation, you can solve it, but you may have already guessed looking at the form. The functions whose derivatives are the same functions are exponential functions, because e to the power something gives you back e to the power that multiplied by some constant. So if you try and solve this differential equation, you'll find df by f is k dx, meaning f is some constant times e to the power kx. Check, no? If you take derivative of this, you are just going to get k times that same thing. So operator acting on a vector gives you some constant with the same vector. So eigenvalues, rather eigenvectors of this operator are functions of the form e to the power kx, and the corresponding eigenvalues are these numbers k that are sitting in the exponent. Let's take one more example. What if I give you the operator, again on the space of functions itself, if I give you the operator second derivative d2 by dx square. So basically I want those functions in which if you operate the second derivative, you get some constant times f. You have seen equations of this sort before. So think about it. If k is negative, this looks like the harmonic oscillator. So you know what those solutions are. If k is positive, you will get different kinds of solution. So you can also find those. So those will be the those solutions that you get. They will be the eigenvectors of this operator d2 by dx square. So the question is, we've seen a few examples now. When we are talking about the vector space of functions, it's still relatively easy because you're just solving a differential equation and you're finding out what the eigenvectors are. But if I give you some random matrix like the one over here in the second example, how exactly do you find what the eigenvectors and the eigenvalues are? So that is the question that we want to ask. So this question, which is also called the eigenvalue problem, is how to find the eigenvalues and eigenvectors of a given matrix. Let's call it omega. So let's see how it's done. The eigenvalue equation that we are trying to solve is omega acting on some vector v, giving you some constant, we'll call it lambda, times the same vector v. This equation, burn it into your brains. You should always remember, this is the eigenvalue equation. This is the definition of the problem that you are trying to solve. You operate this operator on a vector, you get back the same vector multiplied by a constant. So the v's over here are the eigenvectors which we want to find, and the lambda is the eigenvalue that also we want to find. So let's do one thing. Let's bring the right hand side onto the left hand side. So I'll get omega operating on v minus lambda v is equal to 0. Or I can write omega minus lambda times the identity matrix operating on v is equal to 0. So what we have over here, this omega minus lambda I is some matrix. If this was the vector space R3, this would be some 3 cross 3 matrix. Times the vector v. So this vector v, let's say it is some x, y, z, depending what the dimensionality of the vector space is, has to be equal to 0. So 0, 0, 0. So this is like solving a family of linear equations, right? So these numbers over here are A, B, C. Suppose this was 4 cross 4. A, B, C, D, E, F, G, H and so on. So then solving the equation AX plus BY plus CZ plus dw, let's say, is equal to 0. Ex plus fy plus gz plus hw equal to 0, and so on. So you have 4 equations and 4 unknowns. Now, back in high school, when you were looking at how to solve these 2 equations and 2 unknowns, 3 equations and 3 unknowns, and so on, you might have seen this result that this family of equations, this set of equations, will only have a consistent solution. So a consistent solution exists only if the determinant of this matrix is 0. So the determinant of this entire matrix, this ABCD matrix, which is actually our omega minus lambda I, lambda identity, is equal to 0. Only then can you solve this consistently to get x, y, z, w, the unknowns, and which is to get the eigenvector. So this is the equation that we need to solve. Given any matrix operator omega, you construct the matrix omega minus lambda I, you take its determinant and you set that determinant to 0. So you will get some equation in lambda. You solve that equation to find the values of lambda. Those are your eigenvalues. And then from there you can find the eigenvectors. Let's take an example, it will become a little more clear. I'm going to take a matrix, let's call it A, which is given by 2, 0, minus 2, 0, 4, 0, minus 2, 0, 5. Okay. I want to find the eigenvalues and eigenvectors of this matrix. So the first step to do is I'm going to say determinant of A minus lambda I should be 0. What is A minus lambda identity? A minus lambda identity is 2, 0, minus 2, 0, 4, 0, minus 2, 0, 5, minus lambda, lambda, lambda. Basically what you are doing is from all the diagonal elements you are subtracting out lambda and everything else remains the same. So take determinant of this thing and set it to 0. Okay, let's take determinant of this. What is it? It is going to be 2 minus lambda, 4 minus lambda, 5 minus lambda, minus 0, 0 gives 0, and then minus 2 times 0 minus 2 times 4 minus lambda. So I just calculated the determinant of that matrix. This is what I got. So you see what we've got now is some polynomial in lambda. This polynomial is called the characteristic polynomial. I'm talking about this polynomial. Characteristic polynomial of the matrix A. And this equation is called the characteristic equation. So we're going to solve this characteristic equation. So I can actually call this 2 minus lambda, 4 minus lambda, 5 minus lambda, minus 4 times 4 minus lambda is equal to 0. So I can take 4 minus lambda common, and then inside the bracket I have 10 minus 5 minus 2 is minus 7 plus lambda square minus 4 is equal to 0. So 4 minus lambda, 10 minus 4 is 6. Therefore 4 minus lambda, what are the solutions of this? Minus 6 minus 1. So lambda minus 6, lambda minus 1 is equal to 0. So therefore this has three possible solutions. The first solution is lambda equal to 1, or second lambda equal to 4, or lambda equal to 6. So these are the three eigenvalues of this matrix. Good. So we are halfway there. We found the three eigenvalues of this matrix A. Now what we want to do is we want to find the eigenvectors corresponding to each of these eigenvalues. The way to do this is to go back to our eigenvalue equation. Or rather to this equation. We know that A minus lambda identity operating on the eigenvector V should give you 0. So let me just write down A one more time for my reference. A is 2 0 minus 2 0 4 0 minus 2 0 5. So, and we said that lambda is 1, 4 or 6. So first let's find the eigenvector corresponding to lambda equal to 1. For lambda equal to 1, this A minus lambda I operating on V equal to 0, I am going to write this as, so let's from this matrix A, let us subtract 1 from all the diagonal elements. So 2 becomes 1, 4 becomes 3, 5 becomes 4. I've taken 1 out from all the diagonal elements. Everything else remains same. Operating on V. So I'll refer to this matrix V as x, y, z. And this has to be 0. So now we want to solve this equation. Okay. If you notice, now I can do some row transformations. So if I subtract from the third row, if I add to the third row, so R3, I'll add to it 2 times the first row. R3 goes to R3 plus 2R1. You've done elementary row transformations for matrices, I'm assuming. So this becomes 1 0 minus 2 0 3 0, and minus 2 plus 2 times 1 is 0, 0 plus 2 times 0 is 0, 4 plus 2 times minus 2 is 0. Okay, so from this we are ready to solve these equations. The very first row, if you do this matrix multiplication, you get x plus 0y minus 2z is 0. From the second row, you get 3 times y is 0. From the third row, you just get 0 equal to 0. So that doesn't really give you any information. This tells you that y has to be 0. And this only tells you that x has to be equal to 2z. So the eigenvector in this case is going to be y has to be 0, and x and z are related by saying that x has to be 2 times z. So if I take z equal to 1, then x has to be equal to 2. Okay. Now you will say, why did you take z equal to 1, x equal to 2? Why didn't you take z equal to 2 and x equal to 4? Or why didn't you take z equal to 1.1 and x equal to 2.2? Sure, any of those would work. If any vector v is an eigenvector, then any multiple of that is also an eigenvector. So when we are finding an eigenvector, we are not necessarily just finding one vector, we are finding a whole direction for which this stretching shrinking thing works. Okay. So this 201 is the eigenvector. Remember, corresponding to this eigenvalue, lambda equal to 1. We have two more eigenvalues to go through, 4 and 6. Let's do that as well. For lambda equal to 4, so now my a minus lambda I becomes 2 minus 4 is minus 2, 4 minus 4 is 0, 5 minus 4 is 1. 0, 0, 0, 0, minus 2, minus 2. X, Y, Z, 0, 0, 0. Alright, from here what do I get? I get, from the first equation, I get minus 2x minus 2z is equal to 0. From the second equation, I get 0 equal to 0. That doesn't tell me anything. From the third equation, I get minus 2x plus z is equal to 0. When I solve these two simultaneously to get x and z, you can work it out yourself. You will get z equal to 0 and you will get x equal to 0. So for this, the eigenvector z is 0, x is also 0. It doesn't tell you anything about y, which means y can be anything. So I'll put a 1 over there. So this is the eigenvector for lambda equal to 4. And then finally, let's do the same thing for lambda equal to 6. So now 2 minus 6 is minus 4, 4 minus 6 is minus 2, 5 minus 6 is minus 1, 0 minus 2, 0, 0, minus 2, 0, operating on x, y, z is 0, 0, 0. Okay. Once again, I'm going to do an elementary row transformation. I'm going to replace my R1 by R1 minus 2 times R3. I think that will get rid of it. Yeah. So I'll get 0, 0, 0, 0, minus 2, 0, minus 2, 0, 1, operating on x, y, z is 0, 0, 0. So first row gives me 0 equal to 0. Okay. Second row gives me minus 2y is equal to 0, meaning that y should be 0. The third row gives me minus 2x plus z is equal to 0, meaning z is 2x. So now the eigenvector is y is 0, as we've established, and z and x are related by the condition z should be 2 times x. So if I take x equal to 1, z has to be 2. So this is the eigenvector corresponding to lambda is equal to 6. Okay, is that... wait, I have made a mistake. sorry, minus 2, 0, minus 1. Over here I made a mistake. So this should have been minus 2x minus z is equal to 0. So z is equal to minus 2x. So if x is 1, z is not 2, z is minus 2. Okay. So we have found the 3 eigenvalues and the corresponding 3 eigenvectors for a 3 cross 3 matrix.